Hello, I'm Schwa, and if you let me, I'd love to be your math teacher. Today, we're going to be talking about the directional derivative and also the gradient. Those are very related concepts. Now, this is going to be all about, all of this is a part of multivariable, I should have written this down in advance, but this is all going to be a part of multivariable calculus, right? So if you've never done calculus before, for example, then then this video probably isn't for you. But if you're in university, you're taking a class in vector calculus, especially if you're in engineering, you're probably gonna learn this in maybe CALC 3, maybe, but something like that. So this is mostly tailored towards university level students and maybe some high schoolers who are interested in learning multivariable calc. If you're doing that, then I applaud you. Well done. You're doing great. And welcome aboard. But yes, this video might be a bit more advanced than some of my other videos, and I will assume some background knowledge, so that's unfortunate. But basically, the outline of what we're going to be looking at today is we're going to think about this sort of generalized difference quotient. Now, this probably isn't any formal mathematical term that other people use, but I like to always begin the discussion by thinking about the difference quotient and how we can generalize that to multivariable functions. And if you don't know what the difference quotient is, then I will remind you. It should be familiar to you from calculus. We're also going to think about the geometric interpretation of the difference quotient, what it means geometrically. And based on that, we get the sort of directional derivative idea. And while we do all of that, we're going to discover this cool object called the gradient. And we're also going to address the common wisdom that the gradient points in the direction of the steepest ascent. So what does that mean? And why does that hold? We're going to cover all of that in today's video. So hopefully, it's going to be a fun package today. So strap in. Let's have some fun. Let's have some fun with calc today. So first of all, I would like to begin the story with the difference quotient. So just to get everyone on board, and I don't know if I should make more space or just do it here. Let me actually just get more space. I think that's going to be easier for us. Okay, now there's more space. So, we are probably used to the idea that in ordinary calculus, we nudge the input by some amount, and I'm using very, 3 blue, 1 brown-esque terminology here. Of course, there's probably lots of different ways to think about these things, but we nudge the input to the function by some amount and see how the value of the function changes and compare that to the change in our input. And the derivative at a point x, so the derivative of the function f at the point x is defined as this limit, or this expression, as h approaches 0. Now, obviously, this limit doesn't necessarily always exist. Oh, does it not show on camera? Let me see. Okay, now it probably shows. So this limit obviously might not exist, right? And if it doesn't exist, then we say that the function is not differentiable. A function can be differentiable at a point or a function is differentiable at the point x if this limit exists for the given x, and if it's differentiable everywhere in the domain, then we call that function differentiable. Now, differentiability is actually going to be very it's going to be a very challenging concept in multivariable calculus, and frankly, I'm not really going to get into it. So I'm not going to give a super formal treatment of multivariable calculus, essentially. But honestly, more often than not, especially in an engineering setting, we are actually not terribly interested in differentiability of multivariable functions, right? We usually just sort of take that for granted, and then the situations often reduce to the single variable case in a certain sense, and that we'll get to in just a moment, right? But remember that this expression, this limit, we call this expression, right, the difference quotient. So this is the difference quotient, right? It is a quotient, and there's differences in the denominator, and the numerator. So this is difference quotient. Now, of course, okay, I can't write while speaking, but obviously in the denominator here, we could also have like x minus x0, and then have x0 approach x or something like that. So that would be an alternative but equivalent definition, and then we could also have a difference in the denominator here. But usually we don't use that definition, so I'm not using it either. And I think it's going to make our life easier if we actually don't use that definition. So difference quotient. Wonderful. So this is the difference quotient in the 1D case, right? But we're going to get to the multivariable setting now. So I guess the first thing I could ask, actually, like maybe before we get into the, well, you know what? Screw it. Let's get to the multivariable setting right away, right? So we're going to have two variables, right? So we're going to think about the value of the determinant at the point x, y. So we're going to nudge x by some amount. And then, let's take this one step at a time. So let's actually not nudge y at all, right? Let's just do this. Now this right here is a multivariable difference quotient. Now maybe I should write the limit of, let's write the limit of as h approaches 0 here, right? Now first of all, what is this expression, right? This is effectively, even though the function is a multivariable function, we notice that this is effectively we can interpret this as a single variable function and then take the single variable derivative of that function, right? Now, why is that? Well, if we define the function g of x, and let's say that y, that's just some fixed number, so we can define g of x as we plug in the x to f, and then y is just some constant, the y coordinate for the point where we compute the derivative, right? Now with this sort of new definition, we notice that this is actually just the derivative of g at the point x. So it's a single variable derivative, right? So that's interesting. And it turns out that we can actually, this sort of fellow right here, this guy, this individual, we can name them, we can give them the name Doe. I hope this is called, is this called, okay, so I think the character is called Del, but I don't know if it's then called Del F over Del X. I'm not sure, but either way, we have this Del symbol, and basically, whenever we have a multivariable function, right, we use these Del operators to denote a partial derivative, right? Maybe you already knew this, but basically, a difference quotient like this, right, we write very concisely using this partial derivative notation. So whenever you have just alone h in one of the variables, you can take the derivative with respect to that variable, or that's what it means, and then use these del characters to denote that it's a partial derivative, right? Up to this point, there's hopefully nothing that's too crazy. So this, in effect, if y is just, let's say y is 3, then in that case, this would just be a single variable derivative, right? So yeah, not a problem. But what would happen now if we scaled this h here by, let's say, 2, or is 2 a boring number? Let's do 3. 3h. Now, what happens to this derivative? And here, I would actually maybe encourage you to pause the video right now and think about this, right? So this still approaches 0, right? So is this still the same thing? Is this still going to be, the original partial derivative, or is it going to be something else? Pause the video and think about it. Okay, I'm assuming that you've paused the video now, or maybe you didn't want to pause the video, which is okay. It's okay, because I will go over the solution right now. So it turns out that if you go 3 times further, like in the input space, then the sort of change that you achieve is also 3 times as great. So we get a times 3 in here, right? So this 3 is a coefficient here in front of the partial derivative, essentially, right? Now, why is that? Like, do you not believe me? Okay. That's fair to not believe me. I think one way to argue for this is to do a little substitution, right? So if we do a substitution where we, let's see, so we would substitute in h prime, h prime, that's just some new name, h prime equals 3h, right? And we could presumably just consider, put h prime here, right? So let's see. Let me get my eraser real quick. Right. Okay. So let me see. This eraser works. So let's put h prime there, right? So h prime goes here. And this is, of course, going to be h prime approaching 0. And then here, we're going to have h prime. So we had h here. So if we solve for h in this equation, then we get that h is h prime over 3, right? So we can put h prime over 3 in here. And now, this over 3 becomes the times 3 coefficient, right? So that's where this 3 comes from, right? It comes from this 3 over here. Does that make sense? All right, hopefully that makes sense. So it turns out that if we scale these h's in the numerator, then those h's become coefficients here, right? So let me maybe give another example, right? So, or maybe you got the point. Maybe I won't give another example, right? Okay. Now, perhaps the next question to ask. Maybe I should get more space here, actually. And maybe I'll take my eraser with me in case I need it again, because I tend to be very clumsy, so it's good to have my eraser. Okay. So, now, let's consider an even more challenging difference quotient, right? So if we have x plus 2h, right, then we know that this 2h corresponds to multiplying the partial derivative by 2. So let's take a look. So just to remind ourselves of of what we just discovered, you know, maybe it never hurts to have yet another example, right? So this limit, this is equal to the partial derivative. Sorry, let me actually write it a little more cleanly. So it's going to be 2 times the partial derivative of f with respect to x, right? Where the partial derivative, remember, it's defined as this expression without the 2, right? So this would be the partial derivative, right? And this is the expression that we're considering, and it's 2 times the partial derivative because we scale this h by 2 because of the substitution argument, right? Now, what would happen if we also added a plus h to this y? So we're, you know, moving in a crazy direction in the input space, in the domain, right? What would this be? Well, it's actually quite difficult to say like like this, but one way that we can approach this problem is to think about what we would need to add to the situation that we already know how to solve, right? To get this thing, right? So let me be a bit more clear here. So we want to accomplish this expression, right? So x plus 2h, comma, y plus h, minus f of x, comma, y. This is what we want to figure out, like what this is. Now, what if we thought about, you know, what do we need to add to just the x plus 2h situation? I'm running out of space. How do I do this? X plus 2h situation. So this thing. What do we need to add to this thing to get this thing? So this right here, right, this expression, we know that this is 2 times the partial derivative of f with respect to x, right? Because we have this 2h here. So we know what this is, right? And we know how to compute it for most ordinary functions too, because, you know, as we went over, it's essentially the single variable case, right? Maybe I should have given an example of that, but trust me, if you haven't done those computations before, it's going to be very easy. Maybe I'll give an example like at some point in the video. But we know how to compute this, right? And now the question that we could ask is, how do we get from this known result to this, right? And then to to express this, we could just take this known result and add this difference to it, and then we could get the thing that we don't know what it is, right? So in other words, if this difference turns out to be something easy, then in that case, we can just solve for this unknown thing by adding this to both sides. So we get that this thing that we don't know what that is equal to this thing that we do know what that is plus this easy expression, right? Of course, is this going to be an easy expression? I don't know. Let's see. Okay. So let's see what we get here. Let's notice that since there is a minus here and a double minus here, these two terms will cancel out, right? And then what we're going to be left with is f of x plus 2h, and then we're going to have minus f of x plus, sorry, let me think about this. Oh, sorry, I'm missing some stuff here. Let's be careful. Okay, so x plus 2h, and then y plus h. is the second input. Don't forget about the second input. And then minus f of x plus 2h, why is this so difficult? 2h comma y, right? Just like that, okay? Here we go. So what do we have? Well, again, remember that we're at the end of the day, h is going to be approaching 0, right? Now maybe we can assume that this function is somehow continuous, right? So this first input being something that's very close to x, maybe that's the same thing as just having x there because of a continuity argument. So we have to assume that the function is continuous to do this. But in practice, all the functions that we work with generally tend to be continuous. So maybe there's no issue in sort of thinking of this as x, right? But what is this? Well, this right here is just the partial derivative of f with respect to y, isn't it? Right? So like if we have the limit here, so the limit of h approaches 0, and the same limit here, then we notice if f is continuous that this is going to be equal to the partial derivative of f with respect to the second variable, so with respect to y, right? And this is evaluated at the point x comma y, right? So we find that if we add an h to this second input argument as well, then to get from the known situation to the new situation, we add this partial derivative. So this plus h in the y argument contributes a partial derivative with respect to y. Or like more algebraically, we could essentially solve for this expression by adding this to this side to get that this expression is equal to the partial derivative of f with respect to y plus 2 times the partial derivative of f with respect to x. So let me just to be extremely clear, all of this that we did over there, it leads us to conclude that that the limit, the sort of generalized difference quotient, where we have f of x plus 2h comma y plus h minus f of x comma y over h is equal to 2 times the partial derivative of f with respect to x plus the partial derivative of y with respect to, the partial derivative of f with respect to y, so with respect to the second variable, right? And you might imagine that if there was a 5 here as a coefficient, that you would also have a 5 here, right? So the result that we get is that whenever we have this generalized difference quotient with sort of arbitrary multiples of h in the inputs here, we get that the result is summing up these partial derivatives, which are essentially single variable derivatives, where we scale each of them by the corresponding coefficient here in the numerator, right? So this 2 goes here, and this one goes here, but we don't write the 1. So if you've heard of the term linear combination, then we could say that these generalized difference quotients, which will turn out to be called directional derivatives, are actually linear combinations of the partial derivatives of the function. So, let's take all of this, right? Let's take all of this and write it in all of its general beauty, right? Okay. So let's think about this. So, let's say that we have a function that takes in n variables. So, an arbitrary amount of variables, essentially. And let's name them x1 up to xn. And let's nudge all of them with some scaled h's. And these h's, I guess, should I maybe name them? No, they can be h's, right? But let's have the weights of these h's. Let's have them inside a vector v, right? So we're gonna scale the first h by some value v1. We're gonna and so on, and we're gonna scale the nth h by vn, right? And then we're gonna take minus x1. Whoops, maybe I should be very careful with my handwriting here. x1. I don't know if that's any better, honestly. x1, comma, dot, 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 comma, xn. Right? All of that over h. Right? There we go. And honestly, it does not look like it shows up on camera. So let me see if I can fix this up. It's not good. There we go. That's good. You can now see it. Okay. So, now by the previous analysis, and again, like this was stupid. So I had different h's here, but that's stupid. Let's not have that. So we will have a single h, right? A single h, but it's going to be but the h's, they're going to get scaled by different values, right? So that makes sense. And this h is going to be approaching 0, right? Just like that. Okay? All right, hopefully that makes sense. Now, by the previous analysis, we found that this is a linear combination of the partial derivatives of f, such that you weigh each of the partial derivatives with the value that you weigh h by. So we have v1 times the first partial derivative plus, well, let's write the second one. And then I forgot. I'm so clumsy. Let me just write dot, 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 plus, and then vn times the nth partial derivative. Right? Just like that. Beautiful. Okay. Let's see. Perfect. Now, maybe at this point it could be helpful to consider the geometric implications of this. So we know how to compute this limit if h is continuous or something along those lines, right? If h is sufficiently nice is maybe a good way to put it. Then we can compute this limit, and it's this linear combination of the partial derivatives, right? Maybe I should have a quick example of one partial derivative, right? So maybe f is equal to f of x comma y is equal to 2xy. Well, in that case, if you take the partial derivative of f with respect to y, then you pretend that x is a constant and y is a variable. Well, the derivative is just the coefficient here, so that's 2x, right? So that's an example of a partial derivative. And you put in these partial derivatives and you scale them by these values, the values by which you scale the variable that goes to 0. And then that's the result of the limit. Great. So what does this mean geometrically? Well, let's say that our function maps points of the plane into numbers, right? So the input space is like is two-dimensional. So it's there's two variables, right? Two variables as input. So this would be like f of x comma y essentially. And then for each point in the input space, we associate some number, right? So maybe this could be some sort of temperature function that says that at this point the temperature is 5, and at this point the temperature is 3, and at this point the temperature is -1, or something like that, right? And we do that for every point in the input space. Now, if we look at this quantity for some point in the input space, then we basically nudge all of the variables, or we move basically in the direction determined by this vector v, right? So let's say that v is a vector, right? So there's v1 ... vn, right? Then now we can imagine that we move in the direction of v, right? And then this limit is basically saying, okay, let's make this displacement vector arbitrarily small, but let's not make it 0, so let's scale it by this 1 over h here. And then basically just look at, what is the difference between the temperature at a point that is very close to our point, but in the direction of v, and our original point, right? So that interpretation yields us to claim that this thing right here is actually, it is the directional derivative in direction v, right? That's what this is. And we figured out that we can compute it as this linear combination of these weights of h, right? Or this linear combination of the partial derivatives of f weighted by these weights of h, right? Okay, now maybe this isn't making any sense, but here's the real kicker. We can interpret this expression as the dot product between this vector v and a vector containing these partial derivatives, right? So if we think really deeply about what this is actually equal to, then it's equal to the dot product between v, right? So v1 and so on, vn, dotted with the partial derivatives of f. So this would be the first partial derivative all the way until the nth partial derivative, right? And that's cool, right? So we find that to compute the rate of change, or a certain rate of change of the function in the direction of v, we just take the dot product between v and this partial derivative vector, right? And this is easy to compute, right? Because this is just, so for example, if we wanted to compute the directional derivative of this f in the direction 1, 1, then we could take 1, 1 dotted with these partial derivatives, right? And the first partial derivative is 2y, right? And the second one is 2x, right? And then for every, xy point in the input space, we find this directional derivative, which quantifies how much the function is changing in the 1, 1 direction. Wonderful, right? And for convenience, because this vector turns out to show up a lot in vector analysis, vector calculus, we call this vector the gradient vector of f, right? So this is the gradient, and we denote it using this upside down delta, so this triangle symbol, the gradient of f, right? And it's just a vector that contains these partial derivatives of f, right? Not much to it. Okay, cool. And so let me, there's a lot of, stuff here. So let me get some fresh space, and then we're finally going to look at how this directional derivative can be used to think about what this gradient really is. Okay, so let's get some space. Okay, here we have some space. I left my eraser there, but maybe I won't make any mistakes, hopefully. Now, we found that change in the direction of v is quantified in some sense by the directional derivative, whose value is v dotted with the gradient of f, where the gradient of f was the vector of the partial derivatives. Right? Okay. Or maybe the arrow is pointing at the triangle, but maybe it should point at the whole thing. Great. And this is a vector v. Great. Now, let's say that our function is, let's say it takes in two inputs once again. So let's say we're in the input space at this point, right? And now, if we consider all the different directions in which we could move, and first of all, let's be clear that if we make the length of this vector v longer, right? So then the value of this directional derivative increases, right? So if we double the length of v, then the value of this directional derivative also doubles, right? So some people think that's a little problematic. So some people will actually define this directional derivative as something where you normalize this v, right? But I don't like to do that. I think that's just extra work. But know that if you have a problem where you're asked to compute the directional derivative, then depending on who your teacher is and what their preference is, it might be a good idea to normalize this vector v, right? Because obviously, if you increase the length of v, the change in the value of the function, that also gets bigger linearly. But if we just look at the direction, right? So maybe we could have like a unit circle around our point, and then consider all the different ways in which the function might change, in different directions, right? So this v has, length 1. If we consider that, then let's think about this. So is there some direction in which the function locally doesn't change at all, where this dot product would be 0? And the answer is yes. And it is perpendicular, right? Perpendicular, so at a right angle to, perpendicular to this gradient, right? So if this v and this gradient vector are perpendicular to one another, then the value of this dot product is 0, right? That's just a known property of dot products. So if the gradient points in this direction, right? And of course, remember that the gradient could be, the gradient could be, it's not necessarily unit length, right? But we're considering displacement vectors v that are of unit length, but the gradient isn't necessarily unit length. If we consider change in the perpendicular direction or the perpendicular directions, right? There's two directions in the 2D case, and in the 3D case, there's a whole plane of directions in which the change is locally 0. Isn't that fascinating, right? So in these directions, the change is 0 locally. Change is 0, right? But is there some direction in which the change reaches a maximum or a minimum? Well, again, yes. The dot product reaches its biggest value when v points in the same direction as this gradient of f, right? Yeah, maybe this might sound so familiar to some of you. So here, in this direction, the change is biggest. Change biggest. And the smallest value is attained in the opposite direction, because then it's basically the same as the forward direction, but negative, right? So these are properties of dot products. If you're not familiar with that, then it would be a good idea to revise the properties of dot products. But here, the change is the lowest, so the most negative. Change most negative, right? And what we notice from this diagram is that, first of all, there's always a direction in which the function locally doesn't change. That's in the perpendicular direction to the gradient. And that's going to be helpful when we look at how to find the normal vector to a certain normal surface in normal form, I think is what it's called, right? So that's going to be useful, right? But in particular, you know, the thing that you hear repeated a lot in multivariable calc is that the gradient points in the direction of the deepest ascent. So the direction in which the value of the function increases at the most rapid pace. And the reason for that is because the value of the directional derivative reaches a maximum, you know, along a unit circle, of course, right? Because increase the displacement v and the value increases without bound. But if you're just looking at the different directions and ignoring the length of v, then the change is greatest in the direction of the gradient, right? Because in that case, both of these vectors point in the same direction. So in the direction of the gradient, the function changes the most. That's a very important thing to remember, and I think this is a very natural way to come to that result, come to that conclusion. But anyway, I think that's probably about all I wanted to say, right? There's, of course, you know, a lot of computational examples that I could give, and certainly the story, it gets a lot deeper from here. So, for example, now we are equipped to understand Lagrange multipliers, which those are, you know, very cool, very interesting things, and we'll probably look at them in a later video. But, you know, for right now, I think, you know, we've been through a lot, right? So maybe now it's a good time to take a break, chill for a moment, let this all sink in. So, yes, thank you all for watching, and I'll see you in the next one. See ya.